So let's do this. Problem 1 in the exercise set has true-false statements. So true-false statements will be definitely something in which you guys would like to consider for yourself if you can determine whether the statement is true or false, other than just listening to me tell you whether it's true or false. Then as we come to a resolution and have some discussion about it, I can of course guide the discussion and help people draw a correct conclusion and maybe even discuss how you might justify that. Either justifying a true statement with some supportive argument or justifying the fact the statement is false with a counterexample. So let's just start real simple. I'm going to look at A here, just to open up our minds to the conversation about parametric equations. So the first problem gives a statement that says determine whether the following statements are true, or give a counterexample, or give an explanation, or give a counterexample if false. So the first statement says a set of parametric equations for a given graph. Actually, it says curve, so let me try to stick to their language. For a given curve is always unique. So this is the statement. A set of parametric equations for a given curve is always unique. So the question is that statement true? Is it false? If it's true, give some sort of a justification to help understand why it's true. If it's false, provide a counterexample.
I think it's true, I would say.
Okay. And can you give some sense of why you think that is?
I'm thinking because the X and Y would be different. So yeah, I guess that the X and Y equation would be different to get a curve, so it would be unique.
Okay. Let's try to help visualize this for folks a little bit, maybe for those who don't really understand the statement but don't seem to want to ask a question for some reason. So the question is, you have some sort of a curve. So you can just imagine a picture of a graph or something like that. And then you have some equations. And so the question is, and again, for parametric equations, you're going to have something like x of t, or we'll do it this way. The way the book does it is they say x is equal to some function of t, and y is also equal to some other function of t. And that as you allow t to go through its values, and you map the x and y's that you get as pairs, then you get a curve. So this is usually referred to as a system, or in this case, they're referring to it as a set of parametric equations. So to say a set of parametric equations for a given curve is always unique is saying that if you have a particular graph, that there is one and only one. Unique means there's only one. There's one and only one pair of functions for x and y that would give you that graph. And that if you change the functions for x and y in some way, then you would not get the same curve. You would get a different curve. So this is sort of one-to-one for a functional discussion, one-to-one to some sort of a picture. So one suggestion is that this is true because if you had different x and y, you'd get a different curve. I think that's it was Parjit maybe who was saying that, if I summed that up hopefully correctly. Other questions, comments, discussion?
Well, yeah. So I would say it's actually false because the way x and y is being generated is just by t going from 0 to 1 to 2. So if you just like doubled like the rate for both of them, you would still generate the same curve. It's just that t would just get, it would just be that it would correlate to a smaller value of t. I guess that's what I'm. Yes.
No, I think that's a good description. I think that's Tim.
Yeah.
And so if you believe a statement is false and you're trying to sort of explain or visualize conceptually why it makes sense that it might not be true, then the next perfect step to take is to try to formalize that by actually thinking of what's called a counterexample. So you basically described how a counterexample could exist. So the way that no one can argue with that is for you, instead of saying you could have something like that happen, is to provide an example where that does happen. Does that make sense, Timothy?
Yeah. Yeah.
So do you think you could think of a specific example where you could illustrate what you were trying to describe?
Well, yeah. I think the simplest way is just what if we just went like x is equal to t and then y is equal to t plus 1.
Okay, so I'm going to take the liberty of sketching the curve that would produce, okay? So with a little substitution, this is a set of parametric equations. It does produce a curve, so let's see what curve that would be. And if I replaced t in the second equation with x, I would get that y is equal to x plus 1, which is a line of slope 1. So that would give me this line. I made a sketch that I can do here. So that would be the curve that I would get. So questions or comments about how this set of parametric equations produces that curve? Guess I'm a little off the screen here. Let's see if I can do that. There we go. Okay, so that was, so here we have a set of parametric equations for a particular curve. And so to provide a counterexample to show the statement that says this is always unique is a false statement, you would need to give me another set of parametric equations that is different than the one you've given me here, but have the same curve. So can you follow through with that, Timothy?
Yeah, yeah.
So I'm going to maybe erase this one.
Yeah.
I'm ready. You go ahead.
So another like parametric equation that would work is if you just double the t on both x and y. So it's just x equals 2t and y is equal to 2t plus 1. And yeah, and with substitution, you get the same y equals x plus 1.
Okay, great. So we have, these are definitely two different sets of parametric equations because the functions for x and y are not the same functions as they were. If I plug in a particular t value, I get a different x and a different y. For every t value I plug in that's different, except I guess 0 comes out the same. So they, so they definitely are not the same set of parametric equations. And then the question is whether they would produce the same graph. And the argument to justify that that Timothy just provided is that, well, by substitution, I can see that the overall relationship between the x and the y values is that y is still equal to x plus 1. And I think that's a good justification. You could also plot values. You could plot these you know, on a graphing utility. But this is a very good counterexample, and it does show the statement is false. Questions, comments, discussions about that? So one of the things that we talked about when we're looking at parametric equations as a concept is that parametric equations are not only going to produce a graph, but that you can instantly see by simply imagining that t represents some measurement of time ticking away, seconds, months, hours, years, whatever, that not only do you get the graph, but you also can imagine where you are on the graph at a particular point in time, or that the point is moving along the graph in order to create it. And that what can change when you have parametric equations is not only the graph itself, but even with the same graph, the speed or the way in which the point moved around on the graph. So what happens here is that this line is created in the first set of equations over a certain particular point in time, and you're at a particular point on the line based on that point of time. And that in the second set of parametric equations, you basically trace out the line twice as quickly because you go through those same values, but since t is multiplied by 2, that whatever time interval has passed, you've doubled how far along the line you've gone in your point that's traversing the line. So I think there was sort of some examples in the 10.1 graphing homework where they're sort of trying to make this connection between imagining changing t values and traveling along your graph at a particular point in time, and that you can change that. The simplest example of that, that's even simpler than this, simply because we already kind of know the equation, is if you looked at x is equal to cosine t and y is equal to sine t, then hopefully from our work with trig, you know that you get a circle, and that as you let t go through various, you know, radian degree angle measurements, your point is just doing laps around the circle. And as t starts at a 0 and starts at the point 1, 0 on the x-axis, and as t goes up through pi and 2 pi and 3 pi and 4 pi, that the point is just doing laps around the graph of a unit circle. And so as Timothy was pointing out in his example, if I just use 2t in both of these cosine and sine functions, then your point would be just traveling around the circle twice as quickly. It would be doing his laps twice as fast. Instead of needing to go from 0 to 2 pi to go make one full lap, by simply going from 0 to pi, you would go all the way around the circle if it was doubled and multiplied by 2, and therefore you'd go around the circle twice as quickly. Questions, comments, discussions about this first example of a chapter 10 problem from 10.1? Okay, let's clear this and maybe look at another one. Oops, let's get back to black. All right, so let's see in the next little batch of problems. Maybe let's look at number 5. So the instructions are, there's like 4 parts. Part A, plot the following curves, indicate the positive orientation. That was something that was defined in 10.1. B, eliminate the parameter to obtain an equation in x and y. C, identify or briefly describe the curve. E, evaluate dy dx at the specified point. So that's good because these problems cover, you know, several components of what we did in 10.1. And so in number 5, we are given that x is equal to the natural log of t, and y is equal to 8 times the natural log of t squared. And we are told that this is for 1 is less than or equal to t is less than or equal to e squared. And the point at which we're supposed to do the derivative, dy dx, is at 1/16. Okay, so A, plot the curve and indicate the positive orientation. All right, so to plot this, let's get a graphing grid. So in this section, we discussed different ways that we could try to figure out what a graph would be. Now it does ask us in part B to eliminate the parametric to obtain an equation in x and y, which might be one of the ways I would just make the graph. But let's work it a little bit more simply because that is a separate part. So in part A, we're just going to imagine doing this with points and plotting and connecting the dots to remind ourselves how these things work. So to do that, I would sort of make a grid. Oh, sure, why not? For x and y. So in particular, oh, I need one more line. In particular, with the parametric equations, you have your input variable t, and then you have x and y as both being output variables for values that you get. And so we want to remember that our t variable is restricted to this range. So we'd want to be plugging things between 1 and e squared, where we think for t, where we think we could get some nice values, or that we could evaluate them somewhat easily. So first of all, the starting value is 1. So if I plug in a 1 for t, then for x, we get natural log of 1. What's the natural log of 1? For those who are trying to follow along here and participate.
Zero.
Okie dokie. So natural log of 1 is 0. So that means my x value is 0. And in my y value, I'm supposed to square that, take the natural log, and then multiply by 8. So if I square 1, I get 1. Natural log of 1 would still be 0 times 8, so I get 0. So this happily starts at the origin. So there's our first point. Okay, along those lines, if we then say, what's another nice value I can plug in? Well, again, natural log is the log base e. So when you plug in something that are powers of e, then you're going to get nicer numbers. So maybe that's comfortable to do, maybe not. But for example, I could, since we're just trying to see what points we would get, and we don't actually have to plot the input values, let's start simple. Like what if we just put an e to get things started? So if I plug an e into natural log, the natural log of e would be what?
1.
Good. So we would get a 1. And so that's for x. But then I need to do 8 times the natural log of e squared. And we figure out what that would be.
$16.
16, and that helps us because we can see that actually one of the points given on the graph that we're supposed to investigate the derivative of later is 1/16. So if x is 1, it makes sense that y comes out to be 16. And so if I want to plot that, I need to set my scale so that this is doable. 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 here. So I'm going to call that 16. So I have a scale of 2 in the y direction. And then in the x direction, I'm plugging in 1 and e, which is a little bit more than 2. So I'm going to use the natural scale here. So my scales are not the same, just because that's the way I drew this. All right, so I would plot 1/16, and so I'm up here. Well, it makes sense most likely that if I increase my value from there, I get larger values. So maybe I need to even change my scale more. Let's try that. I'm going to cut this in half and say that this is my 16 here, and that therefore up here I'm at a 32. And that means I need to move my point down to here. So there's the point 1/16. All right, so let's go ahead and put the other end of the spectrum because we only have to do this between 1 and e squared. So let's at least put an e squared and see what happens. So any suggestions what I get for x or y if I plug in e squared?
Two.
2 for x, right?
And 32 for y.
32 for y. Okay, so thank you. All right, so then if I go over to my graph, that would be right there. And in this case, I don't want to extend beyond these points because that's the complete range for t, from 1 to e squared. So I can connect those dots. I'm going to observe that this is a line so that I can do this with a line. So that's the graph I get. Now, the last thing is it said to show the orientation. So the orientation, again, are markers on the line that basically show, as the graph is made, which way along the curve the point is moving as it generates the curve. And so in this case, we just going from left to right from when originally we were at 0, 0, then 1/16, then 232. So I'm basically traveling this way with these little arrows. I can indicate that for positive orientation. But I just get this line segment basically, and that's my graph. Questions, comments, discussions about how we generated the curve and showed orientation for this pair of parametric equations for 5a. Okay, so now it tasks us also in part B. So I guess I will erase some of this. Maybe I'll leave up the graphing grid in case we want to use it again. Fun. So there's our graph for the most part. So in part B, it says eliminate the parameter, meaning the t variable, eliminate t, so that we get an equation of just x and y. So here we have ln of t for x, and we have an ln of t in a more complicated environment in the y equation, so we would probably really like to substitute there. So we'd like to isolate the ln of t. So what I would do is I would take this expression and rewrite it so that the ln of is not ln of t squared, but just ln of t. And the way we can do that is, remember that a property of logs is that if you have a power on the argument, you can pull that out front. So this would be the same as 8 times 2 times ln of t, or 16 times ln of t. And now that I have ln of t isolated, I can do my variable substitution for x, and that would give me that y is equal to 16x. And that's a linear equation that goes to the origin with a slope of 16, which is exactly what our graph was. So that's part B. Questions at all about eliminating the variable in the parametric equations? Okay. All right, so I'm going to put these up here again. So we have x equals ln of t, y equals 8 ln of t squared. And let's take it part C. So in C, we're supposed to identify or briefly describe the curve. So that's actually pretty much straightforward. I just did. It's a line. Well, in this case, the proper description will be a line segment that goes from 0, 0 to 232 that connects those 2 points together. Then in D, it says evaluate dy dx at the specified point. So now we have to go back to when we did the derivative in 10.1. So let me give you a page reference for that and look up the formula, because I always switch things around in it when I try to use it without looking. So the derivative, that was in theorem 10.1. So for D, it says find dy dx at, and the point that it asked for was at 116. So on page 714 was theorem 10.1, and it gave us a formula for dy dx. And it basically said you can do this by doing dy dt over dx dt. So that's nice. Actually, I think I will then eliminate these. Now, of course, we know now what this is. This is a line, and this is the point in the middle of the line, and we're supposed to get the slope of the tangent. So we could sort of just graphically recognize that this had better come out to be what the slope of the line was, which is 16. So I'm going to write this as our expected answer. We expect this. Just because we know what this is. This is a simple situation with a line with a slope of 16. So the point, tangent line to any point on this line should be 16. But nonetheless, we can try to use the formula to see it in action and understand how it works. So dx dt, you would just differentiate the equation for x in terms of t, and the derivative of ln of t is 1 over t. And dy dt, we would use the chain rule, ignoring the 8, and then ln of t squared would be 1 over t squared times the derivative of t squared by the chain rule, which is 2t. So this becomes 16 1 over t. And then if we evaluate when t is equal to 1, when t is equal to, not 1, e. So the question is, how do we come up with the point at 1t? So I'm going to remind us that we got this point was at t equal to e. So when t was equal to e, that's how we found the point 116. And so I would, at t is equal to e, then I would get dx dt is equal to 1 over e. And dy dt is equal to 16 times 1 over e. And so therefore dy dx is equal to 16 over e divided by 1 over e, which is 16, as we expected. Questions, comments, discussions about this example exercise problem from 10.1 or any of its 4 parts? Okay. So let's see. So the next batch of problems, they start talking about polar and kind of blending the two a little bit. So let's try number 12. So this is kind of a good place to do these, a good reason to do these kind of problems in this place, because we have problems that tie some of the sections together. So again, I'm looking at page 754 for the review exercises for chapter 10. So let's look at maybe number 12. So in 11 through 16, it says, write parametric equations for the following curves. Solutions are not unique. So they're giving you a problem, which they're just saying you come up with a parametric equation, and solutions are not unique is kind of a piggyback on what we saw in our first true-false statement, in which it said parametric equations for a particular curve are unique. Well, they're telling us here, you're going to come up with parametric equations for a particular curve, but your answers aren't unique because we know that's false. Okay, so in number 12, it says we want to have parametric equations for the upper half of the ellipse and it has x squared over 9 plus y squared over 4 equals 1. So we want the upper half of this ellipse. And it specifies that this is generated counterclockwise. All right, so we can imagine what does this look like now that we've done some conics at the end of the chapter. So this is centered at the origin. Let's do this almost right, and I need a 3×2. And so again, at least leaning on our work that we just did in the conics section that we discussed on Monday. So I can see that this is a squared here, and this is b squared. So a is 3, so that means the semi-major axis length is 3. So that means I would, making a graph, I would go 3 spaces to the right and 3 spaces to the left. And the semi-minor axis length is 2, so I would go 2 spaces up. And we want the upper half, and we want to generate this counterclockwise. So we basically want to go like this. Now, once I've generated it, even though I generated it counterclockwise, you can't really see that that was what happened. You just see what the graph is that you get. Sorry, this is looking thick and crappy, but I'm going to leave it. But I can show that it's counterclockwise by sort of putting these arrow markers on here to show that it was generated in that direction. So again, write the parametric equations for the following curves. Solutions are not unique, and we want the upper half of an ellipse generated counterclockwise. So to not get the whole ellipse, it probably means we're going to put a restriction on a variable. And so why don't I pause there and let you guys think about it and see if somebody could come up with an example. Again, it's not unique, so there's different possibilities. But here's what your goal is. You're trying to find an x of t function and a y of t function. And again, t is a dummy variable. You can use any variable you want. Some formulas for x and t that both depend on t. I'm sorry, x and y that both depend on t. And that somehow as you give some range of t values, you end up generating this half of an ellipse in a counterclockwise direction.
Can we find the sort of constraint, I guess, from A with one of the major axis length A, so we know how far it goes out?
How far what goes?
Let me see, because we're supposed to have a certain constraint on it, right? Because it's only the upper half.
Right, so you're going to have some limitations on your t variable. So you imagine like somehow you plug in a value of t and you get, you know, this first point here. And then you get, you know, a second point and a third point, and that your points are being plotted along here. And that somehow as you go down to the end, you have a final value of t, you know, that is stops there. Maybe if you kept increasing the value of t, you would end up getting the bottom half of the ellipse, but you're just going to basically say, you know, I'm going to say it starts at 0, but it doesn't have to, that you're going to do something like, you know, 0 is less than or equal to t is less than or equal to some finishing value. And that as you let t goes through those values, you get the upper half, but you stop it so that it doesn't go down and make the lower half is probably what's expected. Does that make sense?
Yeah.
Yeah, so the constraint is somehow some limitation on t so that you don't draw any more graph. All right, let's try it this way. Maybe I can give a hint that maybe helps some of you happen to stumble across an insight that'll allow you to understand how to do this. So part of our discussion in 10.4 about conics, when we got to ellipses, is that we said an ellipse is basically a modified form of a circle, and that a circle is an example of an ellipse in which the two focal points have come to the center. So what if we didn't have an ellipse here? What if instead, quick and crappy down here, instead of an ellipse, what if we just had a top half of a radius 3 circle? Then could you come up with parametric equations for that? So that's my hint as a sort of subproblem.
So in the circle example, would that be something related to where we would have like sines and cosines?
Yeah, so the reason I'm trying to refer to this as an example is that when we very first introduced the idea of parametric equations, I pointed out that you've worked with them already when you did trig.
Wouldn't it just be like the cosine t and sine t, but we, instead of it just being that, we multiply it by 3, so the radius is 3.
Yeah, and yeah, in trig, there's formulas. When you're on a circle, x is equal to r cosine theta, and y is equal to r sine theta. So in this case, r is 3, and instead of theta, we're using t. So x would be equal to 3 cosine t, and y would be equal to 3 sine t. Does that seem okay? Like I said, that's an insight. It's remembering some stuff that happened in trig. And again, we've been using trig all along, so hopefully it's not from years ago, but this basic idea. And then having, thought about it when working with parametric equations in 10.1, that the trig functions are examples of parametric equations that produce a circle. So then, since the ellipse is just a modified circle, the difference is just that instead of them both going a direction of 3 away from the origin, in the y direction, you only go 2 away from the origin. So that means that the x value is still determined by 3 cosine t, but now the y variable is 2 sine t. And that's it. Now we do need to get just the top half instead of the whole thing. For both of these, we would be going all the way around. But again, now that we're just using t like we would theta, the restriction is that 0 is less than or equal to t is less than or equal to pi. And then you just get the top half because you restrict t that way. And that gives you the counterclockwise orientation. It gives you just the upper half, and it gives you the ellipse as described. Questions, comments, discussion?
So
Okay. Yeah, go ahead.
in an ellipse, well, I should probably start with the circle. So in a circle, we have same length for your x and your y, but whereas in an ellipse, the y is a little bit shorter than the x. That's why we have an ellipse in this case, right?
Exactly. So as I was saying, circle is just an example of an ellipse where the where the major and minor axes have the same length. And so the reason you have, x squared divided by a squared and y squared divided by b squared is because a and b are different. But imagine that a and b are the same. Imagine that the major and minor axes lengths are the same. Well, then they're both divided by the same number. Well, call that r, because that's the radius of the circle. So if you have x squared over r squared plus y squared over r squared equals 1, well, that's just x squared plus y squared equals r squared, which is the equation of a circle. So when a and b become the same thing in an ellipse, then they are the r that is the constant radius of a circle. When a or b are different, then it's a radial length from the center out to the edge of the ellipse, but it's not a constant length, and it changes as you go around the circle, and it maxes out when you're along the major axis, and it mins out when you're along the minor axis. Does that help at all?
Yeah, that makes sense.
And keep in mind, every orbiting body in space follows an ellipse. And of course, usually the major and minor axes for orbiting bodies that we're used to seeing are somewhat close together, so that the elliptical path looks more circular. But of course, there are many cases in which that's not a circular pattern, and that it's more of an exaggerated elliptical pattern, like with Halley's Comet. Other questions, comments, or discussions before we move on? All right, so this is kind of a nice problem to transition us into doing sort of polar stuff. So let's also do this. It's supposed to be there. There we go. Okay, so now looking at a polar graph, maybe zoom in somewhat so you can see the origin better. Let's just doing that as I anticipate problems coming up. So this is a really good kind of a problem to look at. And so maybe I would try to do this in the book. So let's do this. I'm going to see if I can pull this up in the book because I can't recreate it very easily, but it's a really good thing to get you going with polar. So let's see if I can get us over there. There. Oh, I'm already here. I'll go here. And let's go to Pearson. See if that's going to work. No, not about. And again, so what I'm going to try to do is just go to this page in the book for you guys so you can look at it all together. But if you have the book, we're on page 754 and we're going to look at problem 20. Yeah. So I'm going to go to multimedia library. No. Tools for Success is where we get the HTML version of the book, I think. Wrong again. Course Tools. HTML ebook. And this is page 754, but so can I just put in Go 754? Number 20, here we go. But I can't get the size to stay where I want. So let's see if I rotate the screen, if you guys are able to see that. Still experimenting here. There we go, that worked. All right, so here's the problem to consider. Let's take some time with it. I'm actually gonna give you guys, say, 5 minutes to try to think about this. Matching polar curves, match equations A through F with the graphs A through F. Any suggestions?
I think A might correspond with F.
Correspond with which one?
F.
So Christian likes that. Looks like Hebben, whoever that is. So the comparison was between C or F for R equals 3 sine of 4 theta. So we do know, you could imagine trying to do this a couple of ways. How could you check your answer? How could you sort of match some of these up? So the beginning place to discuss would be being able to literally plug in some points, connect the dots to imagine sketching out a graph and matching with the correct graph. The second way to think about is when you're not creating the graph all by yourself, if you are instead trying to match graphs like this, which would be good test taking strategy to see the simplest way to do that, is you could also, if you're sort of matching between C and F, you could try to imagine what happens for a couple of different points. For example, you see both of these are loops where the loops have a radial length of 3, but they get them at a different place. So one example would be that if you look at on the C graph, you have a point where the X value is 3 and the Y value is 0, meaning the head of the leaf is right on the X-axis where X is 3. Whereas in the F value, that does not occur, that you have to leave the X-axis to get a value of 3. So it might be a question about trying to sort of see how does that point happen. So for example, if I plug in a couple of points, is there a way that I can get it where the R value is equal to 3 when the theta value is 0 or 2 pi, or maybe pi and theta is negative or something like that. So one of the ways is to try to imagine particular points that you would get. So for example, when do you get an R value of 3 for the A function? Whenever the sine function would have been a 1. Or you could, for example, get it to be a negative 1 when the sine would have been, when the sine is a negative 1, then you could get a negative 3 for R, which would work if you were pointing in the pi direction instead of in the 0 or 2 pi direction. So you can kind of try to imagine, would that happen in some multiple of pi? To be at the point 3 for X, 0 for Y, to be at the point where theta is 0, the only way you can get any point in the direction where theta is 0 is if theta is 0 or if theta is pi and you went backwards. So is there any way that theta could be pi or 0 and end up getting you to a value of R value of 3 for the function A? Well, anytime theta is pi or 0, you're going to multiply it by 4 and sine is going to be 0 and you're not going to get that. So that's a way to see that it can't be C, and that instead C, you'd be maybe thinking, well, maybe it's cosine or something like that. Because cosine, when you're at 0, you get a 1, and then if you multiply that by 3, that could work. And that ends up making that the C graph is actually more like E, where you have 3 cosine 3 theta instead. Anyway, so that's sort of a way you could try to check or think about it if that makes sense to you. If not, then you have to think of other options. Now, of course, what most people are going to do as students for our upcoming tests is if you had something like this, you'd like to think you had access to a graphing utility, because then you could just type these in and see which graph you get, because they look different enough from each other that should sort it out for you. Of course, that's not the intent of this problem, but again, I can't help but, I guess, help focus on student success, and students need to make the best use of the tools they have available to them, especially in a testing situation. And since the remainder of our tests are open calculator, open book, open whatever, you want to have a graphing utility and punch these in and see what you get. So it's 11. So we're probably going to have to move this along. So let me just suggest that, for example, if you're looking at the f function, r equals e to the minus theta over 6. Well, the simplest way to point that out is, since r is equal to this value of the e function, that e function is never the same value twice. All the other 5 functions are trig functions which are periodic. So they just keep repeating their values. That means they're just going to keep repeating the same graph eventually. Whereas the r value for function f is not a periodic function. And that means that it's never the same value twice in this case. The e function gets smaller and smaller and smaller as theta gets bigger, since it's a negative exponent. And it gets bigger and bigger and bigger as theta gets smaller. So that's your spiral. That's part A. In fact, A is the only function where the graph is not enclosed, in which you have a graph that just keeps getting retraced over and over again. And so that might be something where you could just observe that fact and make that connection pretty quickly.
Oh, wait, Professor, quick question.
Yes.
In that one where it had r square, would you have to take the square root of that first just to get your r value?
You could do that, but what you'd want to remember is that since you square rooted, you'd need a plus or minus. So that for any particular value on the right, you'd have r is equal to the plus or minus 2 times square root of cosine. Does that make sense?
Yeah, so how would that affect the points though for plus and minus?
Well, because that means that every time you pick a particular angle for cosine that works, then you have to go forward in that angle a certain r value, but you can also go backward in that from that angle the same r value.
Oh, I see. Yeah.
So yeah, so for example, let's say you put in a 0 for cosine, right? That means you're facing to the right along the positive x-axis as an angle, because that's the 0 theta angle. Does that make sense? So
Yeah.
then you get that r squared equals 4. But that means r could be 2 or negative 2. So you need to plot a 2 on the right as well as a 2 on the left.
Okay, I see.
Does that make sense? Are you satisfied by that?
Yeah, that makes sense.
Yeah. So you're going to plug in for theta, and you could do that by solving for r, but just remember when you square root both sides to put the plus or the minus, so that you get that r is equal to the positive or negative 2 times root cosine theta. And then you can also only choose angles for theta that allow cosine to be non-negative, because square root of a negative is undefined. That's already true in the beginning, because 4 cosine theta equals r squared, and r squared can only be positive, so I can't plug in a theta that would give me a negative because there'll be no solution. So there are these things to think about. And basically, hopefully, some of those come up if you just try plotting points and connecting the dots. And that plus or minus all along the way, that means for every theta, there's a positive and a negative r value for that angle. That means you're going to go forward theta and back theta and always get the same number. That is symmetry with respect to the origin. So that was some of the discussion in that first section. The fact that you always have r theta and negative r theta both work when the points work, because r is squared, so it doesn't care if r is positive or negative. Well, that means that it's symmetric with respect to the origin, and there's only 2 graphs here that are symmetric with respect to the origin. That's D and F. Everything else is not symmetric with respect to the origin. And in this case, of course, it's D, because we already figured out F was for A. Questions, comments, discussions about that? Are you satisfied with that, Parjeet?
Yeah, that sounds good.
Okay. All right, so I thought we would look at 23, which says, write this equation in Cartesian and identify the curve. So they give you r squared plus r times 2 sine theta minus 6 cosine theta in parentheses equals 0. And it says, basically convert to Cartesian coordinates and identify graph.
Professor,
Yeah.
what does that say? The question, it says convert to Cartesian coordinate, and what's
Sorry.
that?
Identify the graph.
Oh, okay, all right.
We'll slide
Thank
it there. Yeah, let me make it better. Okay, well, I want to take a break shortly, so how about if I go through this a little bit, those who are working on it, I want to see how this was done. So again, we had some basic equations to go back and forth between Cartesian coordinates and polar coordinates. So let me put up a couple here. So for example, we have that x is equal to r cosine theta, and y is equal to r sine theta, which goes all the way back to trig. In fact, we were just contemplating this a second ago, that if r were two different numbers, then you would get an ellipse. But anyway, for parametric equations. But anyway, so if we have r cosine theta, y equals r sine theta for a particular point, then we can use that here and here. And so that would be a way to eliminate the theta variable and get that part in terms of x and y. So let's say I choose to do that just to start. Then I would get r squared plus r times 2. So sine theta is y over r. And cosine theta is x over r. So I can now simplify a little bit because I can sort of distribute the r here and here. Then I get r squared, and then I get, so these r's both are going to cancel when I multiply by r, leaving the rest. So I'm going to get 2y minus 6x equals 0. So that's nice. And then r is x squared plus y squared. So that's another thing we have over here, that you have r squared equals x squared plus y squared. So if I replace the remaining r squared with that, then I get x squared plus y squared plus 2y minus 6x equals 0. So now I've completely converted it into Cartesian coordinates. And I can just look at that and see it's a circle. Now they might want you to be a little bit more specific about identifying the graph as just a circle. Normally, if you identify a circle, you should say a circle with some particular radius with some particular center. So we'd want to push this a little farther to have proper follow through. But at this point, we're going to get a circle. And the way we can see the radius in the center of the circle is to complete the square. So I'm going to do that. So I have x squared minus 6x. I'm putting the x components together here to complete the square for the x. So to do that, I would have to add 9. And then I have y squared plus 2y. And to complete the square for that, I would want to put a 1. Since I added 9 and 1 to the left side, I have to add a 9 and a 1 to the right side, which is 10. So now that I completed the square, I can write that as x minus 3 quantity square plus y plus 1 quantity square equals 10. So now when I identify the graph, I can be a bit more specific. I can say that this is a circle at the center point of 3, -1 with radius equal to the square root of 10. And here's what it looked like when we converted that. Whoops, not there. There's what it looked like when we converted that into Cartesian. So these said convert to Cartesian and identify the graph. And so we've done both of those. There's the Cartesian, and this is a circle at 3, -1 with our radius of square root of 10.